Hello, everybody. I see a lot of people online who I know and respect. And at this stage of my career, given this huge amount of time, like what am I going to talk about? I think I decided to actually acknowledge people who made me data simulator. And, you know, like nobody is born a data simulator. I wasn't even born an oceanographer. I went to Institute for Shipbuilding, learned fluid dynamics there. They had a short stint at University of Cambridge as a visitor. Met a great guy, Paul Linden, who introduced me to the world of geophysical fluid dynamics. And so like, oh, oceanography is cool. Come back, and it's purely a chance. I come back to my hometown, knock on the door opens, and there's this guy, Gennady Kivman. Some of you may know or remember him because he contributed to FESOM development and data simulation, working on AWI. He's a great mathematician as much as he was a great mathematician as much as he was a great human being. And I was just lucky, guys, like to meet good people who teach me and kind of show me the way and show me the example. And that's why I decided to start with the slide, basically. So we did like a regional model for the astronomical tides, simulated tide gauge data. And then Gary Egbert, another great assimilator from Oregon State, kind of comes to visit us and said like, oh, you guys can do it like 1,000 times as fast because of the representers. That's how I learned about representers. And then I went to work as a postdoc for John Allen and his coastal ocean modeling group. Gary Egbert and Bob Miller were part of it, two great data simulators. And we did a bunch of stuff. So John Allen was authority on coastal ocean modeling and dynamics. He was kind of curious what data simulation can do to us, and that's why he hired me. And I hope to answer his question as well as I could. So we did a bunch of studies on data simulation, scale circulation models. That would result actually in development of the ocean forecast system with data simulation for the Oregon and Washington. We put that online like as early as 2011, I think. Remarkably, are still up and running. So very, very robust system, even though I haven't touched them in a few years. So, but somebody else does. So we did some data simulation studies for the nearshore circulation models. Those are flows driven by the breaking waves, and I like them from the perspective that it's like 4DVAR implementation and very strongly nonlinear flows. And I did a bunch of process studies, but the irony here is that doesn't matter how many process studies and papers I would write without data simulation, people will still continue to call me like John Allen's data simulation guy. So presently I'm working as a physical scientist at NOAA. I moved here because here we developed like truly operational models, they would say, and kind of you can devote more time to development, right? With all of that, let me actually go to my talk. Close this. All right, here's the actual talk. Hold on a second. Let me put it. Yeah, you can see it now, right? So let's talk about this West Coast operational forecast system. The model domain is shown here on the right. Oops, too sensitive. So basically, it's centered on the US West Coast. That's where I spent most of my research studying processes and data simulation. But we also include, you see the mouse tip, right? I can use it as a pointer, hopefully, right? So we also kind of have a piece of Mexican coast. We have British Columbia here. And the reason to include those is because oceanic processes here and there influence dynamics of the US West Coast quite greatly. So why we are doing this, I'm working at NOS, National Ocean Service. As they like to say, our mandate is navigation. So and if you have a model that predicts currents, temperature fronts, salinity fronts, there are a lot of use for navigation community. For instance, currents could be used for ship routing, because like here, I use some imagery from the forecast, and those currents are about like 0.5 meters per second on that particular day. So big ships, small ships don't want to go against those currents. They would rather ride those currents on occasion, right? So ballast water requirements require you to know how close you are to the coastal waters. So they look at salinity. Temperature fronts is a popular product for local fishers, because, like for instance, like tuna fishermen always look for the upwelling front location in summers. That helps them to plan their operations, save fuel, save lives, and so on. We supply our forecast to search and rescue community, to U.S. Coast Guard. They're using our forecasts, also environmental hazard response, oil spills. So the currents from our model drive the oil spill models. The temperature salinity forecast from our model drive the so-called sea harm. It's a statistically based forecast model providing the maps of harmful pathogens in the US, along the West Coast. And also we have examples where our model is used for boundary conditions in a high resolution studies and operational applications. All right. So the model details. The model is based on regional ocean modeling system. It's like ROMS, MOM6, Schism, NEMO, they all solve the same equations, right? So basically the feature about regional ROMS is it uses curvilinear orthogonal grid in horizontal and terrain following coordinates in the vertical. We still like to believe it's the best coastal ocean model because of the higher order numerics that Shepotkin and McWilliams would put there back in the day. So the resolution, we have two kind of implementations. So our target resolution for this project was 2 kilometers. We did a lot of model skill assessments before we started data assimilation. 2 kilometers. We still like it as a research model at that resolution. And the video on the right shows the amount of detail. We are looking at the salinity simulation for summer 2016 here. But we wanted to use 4D for data assimilation. That proved to be kind of expensive for 2 kilometer resolution. Still looking for ways to make it happen. But so far the operational applications for data assimilation and forecast is done at 4 kilometer resolution. All right. So again, like maybe let's use this animation on the right to kind of explain the dynamics. The dominant dynamics along the coast is strong wind-driven upwelling along most of the U.S. West Coast in summer. That changes to downwelling conditions in winter. So in summer, in winter and summer, we have substantial terrestrial discharges, especially in the northern part of our domain, and in upwelling and intensive eddy variability takes that freshened water further offshore, where it kind of merges in the California current system, which goes like further offshore. It's very diffuse, slow current. It's part of the double gyre circulation. So actually, speaking about double gyre, so like kind of this North Pacific current like enters our domain here and separates in the Alaska current and California current system. So basically, that California current system gets freshened because of those discharges in British Columbia and Washington State, right? So before we did data simulation, we did a number of studies to assess the model skill in this model. And those of you who do data simulation know like standard least square estimation is based, it's kind of best linear unbiased estimate, right? So we want to demonstrate that your model is actually doesn't have bias or have little bias. This assesses the bias in the model. So all those papers done with the 2 kilometer version using our best forces like ERA5 and the best boundary conditions that would come from the Navy global model. We use like 5-year runs, 10-year continuous runs without data simulation for this. Basically, we try to go beyond the RMS error computation, also looking at phenomenology. So we looked at the coherence of the coastal sea level along the West Coast, also compared to tide gauge data, looking at like variability from the few days to seasonal interannual. Then we compared to HF radar data, moored temperature, salinity measurements, glider data, everything. Looked at the El Nino effects, and the latest manuscript, which is still in works, submitted, shows the effect of adding GLOFAS terrestrial discharges into this model. Just an illustration how well this model works. This shows the longshore current averaged, or it's the daily non-tidal longshore current averaged over this domain of Oregon. And there are two lines here shown here. The reason you cannot see two lines very well, one is half tone and one is black, because like pretty much on top of each other, even without assimilation. So this is not a bad model by any means. So what makes it worse in real-time environment is because our real-time boundary conditions are not as good as verified boundary conditions and forcing as well. Then we have some deviations. So our ongoing research, as I mentioned, was to improve salinity. And before we do data simulation, we put all the, so our original implementation, I must say, kind of included only major rivers like Columbia River and Fraser River. But then if you look at this European hydrological model, GLOFAS, it shows all those small and big sources along the coast. And if you add all of them, you increase your discharge by the factor of 2. And most of that kind of happens in British Columbia, in Canada, and along the Washington-Oregon coast. So all that terrestrial water, if you compare old model and new model salinity, as shown here in the plot in the middle, in summer, all the terrestrial discharge, freshened water from terrestrial discharges is taken by the eddies in the coastal transition zone, and we can assess, use like in situ data to demonstrate whether we reduce the bias. So this shows the result of the analysis. The curve here shows the annual cycle computed from the area average sea surface salinity in this box. The red is the verification data based on Argo flows. The light blue is our model that has only like major discharges, and after we put all of them, we reduce the bias dramatically. How dramatic is dramatic? We kind of, the bias is equal to the amount of the annual cycle, basically, right? So this is something that will be transitioned in the new generation of the real-time forecast model, right? The next one, data simulation, finally. So when I was invited to work at NOAA, the charge for me was to kind of take the standard community code, which was ROMS, that has the 4DVAR component, and see how far we can go with it, with the community code. So we implemented data simulation. This shows kind of what happened today. So today we did two things. I mean, the real-time forecast model was run to the nowcast and a 3-day forecast for the best initial conditions. The best initial conditions come from the yesterday assimilation cycle. And then at the same time, we run the 4DVAR, trying to improve the initial conditions in the beginning of this three-day cycle. And then we get the analysis run. So since it's a data simulation talk, some details on data simulation details. So the standard ROMS 4DVAR implementation offers only one choice of the model initial condition error covariance, which is univariate. So we don't have any correlations between U, V, T, S, so there's no balanced operator there. But it still works. I'll show how well. We decided we don't assimilate in our real-time application. We didn't have any salinity data. We didn't come to assimilate in situ data yet. So I must say, like, basically they asked me to build that model and see how well it works. It's in a sense, it's like minimum value product. It's useful, but we know how to improve it. So we just use a simulation of surface data, but no salinity yet. Because of that, we decided to reduce salinity error standard deviation to 0. So we basically, salinity is allowed to change only as a result of dynamical adjustment, right? So the data we assimilate include the long track altimeter data, SST from a number of satellites, and we also have HF data that are given us as hourly maps at 6-kilometer resolution UNV, right? What's amazing that NOAA actually pays to support this backbone HF radar set, which is very essential for coastal studies. So actually, given that and the fact that the present ROMs can only simulate instantaneous data in space, instantaneous data and local data in space, we were concerned whether HF radar simulation will be very effective, because the HF radar data which we assimilate is hourly instantaneous data, so they have a full spectrum of flows there, from interannual to seasonal, wind-driven upwelling, and also internal tides, inertial variability. So this high frequency variability, internal tides and inertial, can be very energetic, but it's not necessarily predicted by our model well. So despite that, 4DVAR kind of filters out that maybe treats as noise, so we are able to improve forecast for the daily average currents, which was pretty encouraging to us. The first step, so the example here shows the time series of the RMS error for the daily averaged HF radar data. So this is the data we haven't assimilated yet. So like the next cycle data. So before we do assimilation, we compare to that data. So the red line is the time series for the NOAA benchmark solution. And the green line is reduced RMS error after we assimilated the data for the previous days. Right, so we improved the longshore currents, which is nice. Also, kind of no-brainer, we assimilate satellite SST and we improve SST compared to in situ buoy data. We have all those buoys. Thanks to Parisa, by the way, Heidary, who's here on the call, for doing all of that hard work. So somebody may say like 1.5 or 1 centigrade improved RMS error is a lot, but I should remind you we are working on very strong upwelling system. So we have the upwelling front developed in summer, and you have like at least 10-degree difference in temperature across the front. So so our ongoing challenge is constraining sea surface salinity, and that's what I'm kind of want to give you some details about. So we don't assimilate salinity, and we don't allow to we don't change salinity instantaneously at analysis step. All of that is a result of dynamical adjustment to everything else, right? Despite that, we see that our data assimilation solution develops the wider salinity front. So we control the front in terms of temperature by assimilating temperature data, but we don't constrain the salinity front, right? So wide, and this front is wider than the front in the model without data assimilation. We have glider data to judge which solution is better. And turns out that non-DA front is actually, in terms of salinity, is better than the data assimilative solution. So that's the challenge. Why it happens, maybe for a number of reasons. One of them is that everybody brag about the data assimilation increases eddy variability. We put the eddies in there, hopefully the right amount. The question is like how much is not too much, and maybe enhance horizontal eddy transport of upwelled waters in this data assimilation system, take the salinity further offshore than you would like to. So the immediate idea, or maybe now we have this satellite salinity, and I'm part of the NASA Ocean Salinity Science team, so we kind of start looking at that as part of that project. You find immediately, well, these two plots are on the same color map, and you find this is much fresher, this particular product on this particular date. And this is like, we've looked at a number of products, and this is kind of the best product we like to work with these days. I would say we try to evaluate that bias, and we have a number of data from a number of gliders provided by Dan Rudnick and the University of California, San Diego. Awesome data set. So we take the top beam of that from that glider and basically run the kind of glider through the SMOS product and compute the bias, and we find out that bias is actually seasonal. So we on average have SMOS give you saltier SSS in winters and fresher in summers in this part of the world. So the way to proceed here, probably to find a way to debias it somehow. Despite that, we decided kind of, let's just build the infrastructure, just kind of assimilate it, even though we know it's biased product. And biased by a lot, by like 0.3, 0.4 PSU sometimes. And recall, like before we didn't assimilate any salinity data. Now we try to assimilate it, so we have to actually allow error, assume the error in the salinity part of your initial conditions. So we kind of stick from the, basically we're changing two things. We now include the salinity data and we change the covariance. Just bear that in mind if you try to understand what happens next. So, okay, now we assume like 0.2 PSU at the surface. We have exponential decaying profile for the standard deviation of errors in the vertical, and compared to that, the standard deviation in SSS observations, I assume to be like 0.1, right? So, of course, when we assimilate, we increase the error in salinity, especially in northern part of this subdomain. So our domain is bigger than this map, but that influence of fresh water is probably kind of what freshens our solution more than necessary. That's why if you look at the time average April through October 2024 RMS errors for our forecast versus the glider that we don't assimilate, right? So the glider goes back and forth quite slowly here, but over April, October, we collect quite a few a few sections that we basically sample our forecast solutions, like kind of from the virtual glider to compare to the glider data. And then we average in a cross-show direction and time, and again get those RMS plots for each of those lines, 56, 66, 80, 90, from north to south, right? You see, like, so basically there are three lines there. The NOAA is red, the data assimilation without salinity assimilation is green, and the golden color is data assimilation including surface salinity. So like at 56, we actually make our data simulate our salinity worse because we freshen too much. The rest of them we kind of closer for some reason. They're kind of surprising and curiously what happens there, even though we don't improve salinity profiles, we by allowing error in the salinity and also by simulating salinity of the surface, we improve our temperature profiles compared to the glider data, right? So that's kind of curious result, and this is very ongoing project. We also had the idea to maybe kind of estimate the annual cycle in salinity and just match the solution to that. But if any of you wants to go that path, this is like a, kind of the note of caution. It turns out the interannual variability in salinity can sometimes be larger than the annual cycle, right? The example is here. So our initial analysis that I showed you earlier considered like 2010 through 2018, and salinity was kind of had some seasonal variability here in this box of British Columbia in Canada as before, right? But then we decided to look at later, more recent years, and we see this continuous decline in salinity from 2018 to 24. Something like people a little bit overlooked, I think. It's a big signal, but because it's not temperature salinity, kind of there was not as much exposure in the news about this. We looked at a large scale picture. If you take summer salinity, summer 2024 salinity minus summer 2018 salinity, you have this like pattern that painfully reminds you of patterns of the long period variability over the West Coast. And now our ongoing study with Bahram, Khazaei, we trying to connect this variability to the most of decadal variability like PDO and also variability in the strength of the Pacific giant stellations. This is not just the surface event, so those pictures mean to emphasize that the anomaly kind of develops from 2019 to 2025. And that anomaly in salinity extends to at least 200 meters. So it's a big event that's part of like PDO and PGO variability. Again, like for our data simulation, the point here is that interannual variability can be larger than annual variability for salinity, which is not necessarily the same for temperature, right? So, and this is pretty much where we are with this West Coast project. I want to spend a little bit of time until as much time as I have to kind of discuss with you what else we would like to do. And some of those ideas we tried in our earlier studies using this precursor of the WCOS, our beloved Oregon-Washington model. So in this domain, for that model, I should say we didn't use RONS 4DVAR. I used my own tangent linear joint codes. Kind of we tried to build a system that's uses RONS as a nonlinear driver and use our tangent linear joint. Everything was kind of very modular, pieces connected to using C shell scripts actually. So it's kind of precursor of the JEDI, if you know what JEDI is about. The same idea. And that would allow us to use like more flexible choices about how we treat the data and what kind of background error covariance we can allow. In particular, Ivo Pasmans, who was my PhD student, I was honored to have that guy. So everything he developed was his independent work. My job was just to understand what he was doing. And he did basically this whole methodology for the ensemble of 4DVARs, essentially, done very effectively. We had like 14 ensemble member that he would run for the price of 4. If you want to know how he did it, read the papers. So because of that, we could assess kind of the impact of the balanced operator versus ensemble for DVAR. But before I get to that, if I get to that, so I want to mention, we want to assimilate data's time average, which is essential for altimetry, HF radar UV. We don't want to fit our data to those very energetic internal ties, like half a meter, fastly moving waves, for instance, right? So the way to do it in a joint model, so if you assimilate instantaneous and time data, so this is the timeline just to give you kind of flavor of it, and also the flavor of what FODVAR is about. So you start from your computation with a joint integration backward in time, and then you hit basically at the impulse at the observation location in time, right? That's kind of standard. But if you use the, if you assimilate, it's still like one observation, but it's time average. So instead of kind of hitting it at one time instance, you kind of spread that impulse over the number of time steps. All right. So it's much more gradual introduction of that impulse. So we tried it with our small model, and actually, as we speak, the ROMs developers trying to make that capability available for everybody in standard ROMs. So another thing that's not in standard ROMs, but like to have it, we tried it back like 2011. So assimilation just trophic slope from altimetry. So right now we assimilate SSH. You have to match the mean levels in the model and the data, and that's pain, right? That's pain. You have to really be sure that your geoid in the model is the same as geoid in the data. And the other thing I want to kind of discuss with you guys, and if anybody has a comment about this, I'll appreciate. I have this, I'm not a mathematician, don't have like the proof of that, but I have the feeling, given especially like very limited number of iterations in FODVAR, when you, basically we have like 7 iterations and 2 outer loop, 7 inner loop. So basically our correction lies in a state space of 7. So I think data assimilation tries to find the most energetic correction. And when you try to assimilate SSH data, if your mean levels don't match, SSH data tries to correct the mean level, first of all, but your mean level in the forecast is totally determined by your boundary conditions, because so basically whatever correction you made to the mean level, it just goes to gravitational waves, and flutter conditions happen, help to the disturbance to move out of the domain. So if you assimilate the slope, like just trophic current, so you don't try to correct the current, but you can try to correct the just trophic slope in your data. So I think it's much more effective way to actually put the edges in the right place in time. So again, like from the standpoint of a joint, so if you assimilate SSH, and this is an altimetry track, so the time of the observation, you hit your joint model, you add like impulse to the joint solution, then you go backward to get sensitivity at initial time, right? So if you use SSH slope assimilation, you kind of force a joint not with the impulse, but like a long track derivative of that impulse, if you like, right? Very elegant from my perspective, and it works. So again, from that very old paper, how well it works, we had this experiment, compared 2 experiments, no data assimilation, and the experiment where we assimilated only a long track altimetry, only the slope. We didn't even assimilate SST in this experiment, in this test. I showed you 2 maps. The map on the color in each map is the same. It's SST from the satellite, right? And the contours here show the contours of sea surface height after we made quite a few assimilation cycles. So basically, we did a simulation experiment over like spring, summer, and this is like end of experiment, end of September 2005. So the lines are close to each other. This is where the coastal current is. So our low resolution model actually doesn't kind of show a lot of separation here, except like it starts separating vigorously at Cape Blanc at 43 north, right? And those are points like 1, 2, and 3. This is where we see those patches of colder water, which is the result of separation. So basically, this pattern may kind of explain separation at point 3, but it doesn't explain separation at point 2 or 1, because like there's no connectivity between those contours and those points. After we have assimilated SSH, just SSH, we have the SSH field that does explain those separation points, right? And also it helps, it has very interesting implication for the subsurface structures as well, because we put that current that used to be like very close to the coast, we move it like 300 kilometers offshore more, and the subsurface structure adjusts to it by the thermal wind balance actually. So actually the last thing I want to show before the Q&A is something about background error covariance. So in present ROMs, as I mentioned to you, we have the univariate covariance, so errors in SSH, temperature, salinity, UNV are not correlated. In our ROMs Aurora implementation, the standard implementation, we use the balanced operator, thanks to Anthony View. I see like Anthony here online. So we made correction there, modification to allow to use the balanced operator over shallow water where you don't have the reference no flow level, right? So, but the sense of the balanced operator is like your model error covariance, your initial condition error covariance is kind of it's combination of this, like D transpose times BT times D. D is a dynamical balanced operator. So in our case, if you kind of assume you have error perturbation and temperature, you kind of try to use all sorts of dynamical ideas, geostrophy, thermal wind balance, this and that, to deduct everything else, right? And BT is a univariate covariance for the temperature error. So that's how it worked. Not without shortcomings. And the shortcomings not become because of the idea of the balanced operator, but because of our implementation, possibly. The first thing in building this operator is to kind of connect the changes in salinity and temperature. We tried something more complicated. It was not stable. So we reduced it to very simple statement, kind of linear relation between temperature and salinity perturbation. That was taken like from the TS diagrams, like here in the lower left corner. This is based on glider data of mid-Oregon coast. So it did show like during strong upwelling season, it's like a straight line. But in the beginning of the upwelling season, it was like more variable, right? It's shown like on the top here. So again, like top left is also data early in the season. So, and if you do use our balanced operator simulation that makes this assumption, after a few cycles, you start kind of building this like branching and TS relation in your forecast that basically build as a result of balanced operator. This has nothing to do with reality. So Ivo Passman had this ensemble 4D-var solution where the covariance comes from the ensemble of solutions, and it helps us to solve that problem. And also it's sensitive enough when we go to proceed with the simulation late in the season, kind of the system is sensitive enough to recognize that now actually you're on a straight line, right? So kind of using this ensemble of 4D-var is really kind of, in my view, is a way to go for us in the future, right? With all of that, let me conclude. So WCOFS is operational forecast system built by NOAA. It's a Pathfinder system. It's not ideal. It's kind of our minimum value product, but still does skillful prediction for surface fields that have been used by people. Our challenge is salinity as of today. That's what we would like to work on. And all those next steps that we discussed, I would love to see them move to the WCOFS reality in my lifetime. And I'll stop here. Thank you very much.
Yeah, thank you very much, Alex. We have two questions, both from Dan Leah. Before I come to Dan's question from my side, are there actually concrete plans to bring any of these more modern developments in this operational system?
Well, as we speak, Parisa, who is here on a call, is testing assimilation of in situ data, right? We also yes, this is easy. This part is easy with the present ROMs. Daily average assimilation, Hernan Aranga and Andy Moore are about to release it. They are testing it. So this will be coming this year. So we'll have to see if that helps us to reduce the noise, kind of reduce the spurious edges maybe, and reduce the salinity problem. The rest of that, not in plans or in plans. And if anybody has the 4D-var on GPUs already, give me the call. We'd like to use it. So I think that's the way to go for us. Until then, we'll play with it. So that's my other kind of funny pet project. All right.
Okay. Thanks. Yeah, let's come to one of Dan's questions. I think the second one you maybe can answer then by writing. The first question Dan wrote is, there are quite long lateral boundaries for this model. Do these have a strong constraint on the interior solution, or can the data assimilation then still have a strong impact in the interior?
Yeah. All right. I must mention, like, the strong float divider was created by Andy Moore, Hernan Arang, and Rutgers University group, like John Wilkin, and they would actually implement technically the boundary, open boundary correction is in there. Whether you are using it or not is a matter of philosophy. All right. So for us, imagine that there are coastal trap waves propagating along the coast, right? And if your initial correction is not correlated with the boundary condition correction at the initial time, then you actually have the step that will propagate as a coastal trap wave. So I kind of aware of that. We kind of have theoretical analysis of that and kind of a memory of that work. I try not to correct initial conditions. We have never tried. Partly that's why we put that boundary so far away. We also did the analysis that show that like 5-day variability doesn't affect our currents. 5-day variability at the south boundary doesn't affect our currents too much. US coast, and like 20-day variability is very well represented in a Navy product that we're using as a boundary condition, right? Yeah.
Okay. Yeah. In the meanwhile, also Phil Brown put in a question, but maybe you can write answers since we are slightly behind in time. So yeah, it's 37 minutes of this time slot. So thank you very much.